In the next section, we're going to just practice reading graphs of functions and finding domain and range of functions and some other miscellaneous topics that are in there that are related to graphs. Before we do all of that, we're going to first talk about just being able to tell if a graph is a function or not to begin with. So we want our functions to be defined so that y is a function of x. And it's hard to see on these graphs, but you know, this is x and this is y. And mine didn't print correctly. You should have, if yours didn't print correctly, you should have had something that looks like this on the graph. This one showed up and this one didn't. I don't know why it does that sometimes. So the question is, which one is a function? So if we keep in mind that a function is a rule that when you put in the input, you get at most one output, right? You might plug something in, but it's not defined, and then you wouldn't have a point there at all. But like, for example, in this function, when you plug in 1, the output looks like 1, right? And so there's only one output for the input 1. In this one, when you plug in 1, you get out 1 here, and you get out -1 down here. So this one is not a function because for the same input, we have two different outputs. We can generalize that idea and just say, well, anytime we have two points stacked vertically, then we don't have a function. And that's what most people call a vertical line test. So it's just this idea that if you could think of a vertical line anywhere on the graph, if you're gonna if your vertical line intersects the graph more than one time, then you don't have a function. So if every possible vertical line crosses the graph at most once, then you do have a function. Okay, so it's at most once, one time. It could maybe in some spots not intersect the graph at all, and that's okay. So the first example, this is obviously a function. If you I just say use a straight edge or use your pen or pencil, run it across the graph, and of course everywhere we either don't intersect or we only intersect one time, so this one is a function. So the vertical line test is a really easy test. You can quickly tell whether or not you have a function. Then the domain and range. Remember, the domain is the set of all possible inputs, and the inputs are your x's. So what you want to look at here is, for a given x, do you have an output that pairs up with that input? So -6 is not in the domain because there's no output. The function is not defined at -6. So what I like to do is to think of, again, that vertical line, and the first time you touch the graph, that's the first number that's in your domain. Now I always go left to right because we want to go smallest values to largest values. So the smallest number that's in the domain here is -5. And we'll use a D for domain and a colon to show we're talking about the domain. And we're going to use interval notation. -5 is or did I say -5? Because that's -3. Sorry. So scratch what I said before. The first number you hit is -3. And that is included, so you use the squared off bracket to show -5 is, so I did it again. -3 is part of the domain. I don't know why my brain is doing that. Okay, and then once you get greater than -3, now all of these points or values are in the domain because you have a point that corresponds to it. There's no jumps here. And the largest value that's in the domain is 2. So you can kind of see that this graph is completely sandwiched between -3 and 2, so that's the domain. If you shifted this graph up 1,000 units, the domain is not any different, as long as you don't slide it left or right. Okay, so think vertically for domain. And then for the range, now these are your set of outputs. Your outputs are the y-coordinates. So here you want to look at a horizontal line. Start from the bottom because you want to go, again, smallest to largest. And notice there's no ordered pairs down here. That means you don't have any outputs that equal -4 or -3 or -2. the first output that's possible for this function is -1. So we'll put R for range, and then -1 is part of the range, so again use the squared off bracket. And then from there you've hit a value the entire way until you get to that 7 there. So 7 is the largest number in the range. I should have said this before, but these, closed circles mean the graph stops. It doesn't continue beyond those circles. Okay, make sure I answered both questions. Yes, okay. So let's do this for some more examples here. I don't know where this came from, but just ignore that. So this one is not a function. We can see if we do the vertical line test, it's going to fail, right? Fails. So no, not a function. And if it's a graph, a reason, and I ask for an explanation, you can just say that it fails. I'm just going to abbreviate vertical line test, VLT. That would be fine for a reason. It fails. All right, now domain. So again, you're looking at your x's. Notice this is, now even though it's not a function, we can still discuss domain and range. It doesn't have to be a function to have a domain and a range. So there's nothing in the domain here. The first thing in the domain is 0. Here we have x equals 0 at this vertex. So the domain, the smallest number is 0. And then once you get past 0, all of these numbers are in the domain. The arrows show this keeps going, so that's going to include all positive numbers. It doesn't matter that you have 2 outputs for the input. That just means it's not a function. But it doesn't affect the domain. The 4 is still in the domain. You have 2 ordered pairs that have a x-coordinate of 4. The range, now again we're looking horizontally, left and right from the y-axis. If you see the graph, it's in the range. So here, everywhere you are on the y-axis, right, that number line, if you look, in this case it's always to the right, you're going to see a point. And then of course this one's actually on the y-axis. That's okay. So the range for this is all real numbers. I don't know if you can hear that music in the background, but my office next door neighbor has some loud music. I might have to get him evicted. I'm kidding, of course, but it's a little annoying. Okay, so I don't know, maybe you can't hear it. I hope not. So in this graph, again, go this way vertically. Now this almost looks like it goes vertical, but it actually doesn't. It's going to keep slowly going to the left. So as you draw your vertical line from left to right, you're going to hit a point at all times. So the domain is all reals. Whoops, and I forgot to talk about whether this is a function. And since you only hit exactly one point as that, if you draw that or move that pencil across, this would be a function. That should be, easy to see. Okay, so the domain is all reals, and then the range, going the other way, horizontally, notice you're always going to hit a point. So it doesn't matter if you hit things more than once. You got 3, like for 2, there's actually 3 different x coordinates that give you an output of 2. That's fine. You don't need to list them twice. It's just the range is all real numbers. You heard somebody knock on my door and I ignored them on purpose because I'm in the middle of a video. Okay, now in this one obviously would fail the vertical line test, so that's not a function. Again, fails vertical line test. I'm not going to write that every time. Then the domain, going this way, you can see this is all bounded in this circle. So the smallest x-coordinate is -7. And the largest x-coordinate is 1. That's a 7. Okay, and then the range, going horizontally, the first time we hit the circle is when y is -4. And the last time we hit it is when y is 4 up here at the top. All of those values, those points are on the circle, and so you include the numbers. In this one, this is a function. If you drew vertical lines all the way across the page, everyone would hit at most one time. So function. And then the domain, we've got, so this is an arrow going to the left. So that means everything, all of these negative numbers, you know, keeps going on forever, are included in the domain, and it stops at -5. So we'd say negative infinity to -5, and the open means that this is not included in the domain. So if say this was y equals f at x, if I asked you what's f at -5, that is undefined because we don't have a point there, right? If the point was solid, then we would say it is equal to 6, but the open circle means everything up to that is included, like -5.001 is on the graph for x, but not -5. So to show that, we use the regular, you know, rounded parenthesis. That tells us -5 isn't included, but everything up to it is. And then we have a jump here. Like, see, there's no point for -4. And we start up again at -3. So to show that this is, you know, there's a gap, we're going to use the union symbol and connect these intervals with that union symbol. And now we've got -3. And that, you know, your pencil is always hitting the graph now all the way up to 8. It stops at 8. And 8 is included because of the closed circle. All right, now for the range. We're going to go this way. And so the first number in the range is right here, -5. That's on the graph, so that's included. And then this, what will happen with people is their eye gets drawn to these points. But that isn't where you're going to stop, because notice you're still hitting points here. It stops at 4, and then we have a gap. There's a gap in here, right? So the 4, doesn't matter if you hit points more than once. You don't need to list things twice. You don't even want to look at those points. You're hitting the graph everywhere in here horizontally. So -5 to 4, then union, and then again, this arrow like makes you think it's a range of values, but if you're looking at it from the y-axis, say you're like standing here, say I turn it this way and you're looking up in the sky, straight below it, you're only going to see one dot, right? You're not going to see that whole range of values. And so really this is just the value 6 for y. The range of values comes with the x. And so since it's not an interval, we use a bracket symbol. It's just the number 6. And once you get past 6, now those numbers are not in the range again. That one is a piecewise, you know, or, well, we could write it as a piecewise function because we have this gap here. Okay, example 2. Now, I'm telling you this is a function. If we use function notation, it has to be a function. We wouldn't use this notation if it were not. And this one printed out fine. This is what it was supposed to look like. All right, so we want to find f at 3. That means let x equal 3. I don't have the numbers on here, but just assume everything's 1 unit. So 3 is here. F at 3 is 2. That's this point right here. So that's the point 3, 2. I don't want you to put 3, 2 here. F at 3 equals 2. The output is y. You should not answer as an ordered pair. Okay, f at -4, 1, 2, 3, 4. Here's -4. The y coordinate there is 3. F at -4 is 3. F at 8. 8 is way over here, right? This biggest value in the domain is 4. So f at 8 is not defined. Or you can just write undefined. If you want, you can write does not exist. DNE for short. That would be fine. D. Okay, so in these first A through B, you're given the x and you find the y. In D, you're given the y. F at x stands for y. Find all of the x that give us this output of 1. So the y is 1. Here's 1. Notice there's actually 2 points that give us an output of 1. Both of those points have a y coordinate of 1. The x's are 0 and 2, right? That's 0, 1, and that's 2, 1. So there's 2 answers to that one. Domain, so again, left to right. Smallest value is -5, and the largest is 4. There's no gaps in between. You hit a point everywhere in between. And then the range, again, don't look this way. Looking this way, the smallest is y is 0. And the largest is here. It doesn't matter that you got this, line. 3 only needs to be included once. So 0 to 3 is the range. All right, well, let's talk about this concept of increasing, decreasing, and constant. So I've got these kind of fancy looking definitions here, but the definition makes it look more complicated than it really actually is. So I'm going to draw a picture to explain this. I'm just going to use the first quadrant. And so you have your x and your y. And so this is saying you have two x values and x1 is less than x2. So when I draw my picture, that's the way I'm going to draw it. I want x1 to be to the left of x2. I don't have to be in the first quadrant, but it's just easier to see the picture if I don't have this intersecting it. So whenever this is less than this, then the function value that matches up with x1, that's called f at x1, is going to be below the function value for f at x2. And so what happens is, basically, if you read your graph from left to right, the outputs are going up. In other words, you've got something that's increasing. As x gets bigger, y or f at x also gets bigger. Doesn't have to happen on the entire graph, and that's what this open interval part is. It could change, but at least for part of it, right, it's increasing. So like in our previous example, this part is increasing. Always read from left to right. So if the graph is going up from left to right, that's a part where it's increasing. Decreasing then, well, you probably can guess what that's going to look like. You still have, you're reading from left to right, x1 is less than x2, but this time notice this flips around. The function value that matches up with x1, your y coordinate, is actually bigger than the function value for x2, so it's got to be above it on your graph. And so what that means is, as you're reading this from left to right, the graph is going down. Let me say that's decreasing. So again, that doesn't have to be for the entire domain. It can just be on some part, some interval on the domain. And then the third thing that can happen is that as you're reading from left to right, all of the function values are the same. And so in this case, I'm still going to draw x1 less than x2, but it actually doesn't matter which order you put these in, because all of these things in here have the same y coordinate. And that's constant. So for constant, you've got some part of the graph as a horizontal line. So in the example we just did, we had a constant part, a decreasing part, and an increasing part. Always read from left to right. Now I give a different example here. Let's do this one. So here we have this function. Now this does pass the vertical line test. This is fine. We don't, for 2, we don't have 2 points on the graph because one's open and one's closed. So this does pass the vertical line test. We're calling this g at x, and it says find g at 0. And g at 0, well, here's where 0 is. So what's the ordered pair that is on the graph when x is 0? It's this one. So that means g at 0 is -2. That's where y is -2. G at 2, here's where a lot of people make a mistake. They put down 2 and 3, but this is actually the only point that's on the graph when x is 2. There can only be one output if we have a function, and that output is 3. So this one's not on the graph. Don't say g at 2 is 3. Whoops. Did I just say don't say it's 3? I meant to say don't say it's 2. Sorry. Sometimes the words don't come out right with me. I'm sorry. So g at 2 does not equal 2. It's 3. Okay? All right, and then the intervals where the function is increasing, decreasing, or constant, we're always going to give these as open intervals. So let me start over. We're going to read left to right. So first it's going up. That means the function's increasing. So even though this is included, we're not going to put a bracket around -3. We're just going to say increasing on -3. And when you do this, these intervals are intervals on the domain, okay? Don't even look at the y-coordinates. This could be shifted up a million units and it's the same answer. The y's don't matter here. It's the intervals on x, okay, or the intervals on the domain. So looking at x, it starts at -3, it's going up, 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 and it stops at -2. So I said -3 and I wrote -2. Did it again. Okay, so it starts at -3, stops at -2. Now it's decreasing. And so it's at decreasing on starting at -2, stopping at 0. Then it starts to increase again. So up here we can just say and from 0 to stops at 2. And oh, actually we don't have to stop at 2 because here it's still increasing. So 0 to 4, and we can just include that as 1 because this is still greater than, it still goes up. Doesn't matter that there's a jump there. 0 to 4. Okay. I was gonna, sorry just for saying so much. I thought I had something I wanted to say, now I don't remember. Oh, I remember what it is now. This right here, this is where a lot of people, when I said don't look at the y's, because they see this -2 and they want to use that. But the x is actually the 0, right? So the change from decreasing to increasing here occurs at x equals 0. Don't look at the -2. Okay. Moving on. So we have these 4 definitions for minimum and maximum values. This, looks kind of long, but it's not that hard. It's kind of like the increasing, decreasing. The definitions look tedious, like really detailed, but it's not that difficult of a concept. Okay, so we have this function f, and then we're talking about one of the function values. And we can talk about maximum and minimum values. So like in this graph here, when we were decreasing and then increasing, we reached a bottom point, right? And so that's a minimum. Well, there's different types of minimums or maximums. If we had flipped it around, it would have been a maximum. We have absolute or global extrema, just generally, maxima and minima. And we have these relative or local maxima or minima. So the absolute ones would mean you're at the absolute very bottom point on the graph or very top point on the graph. And so the max would be this function value here is bigger than or equal to every other function value on the entire domain of the function. So I'll just draw an example. Maybe it's like a parabola that opens down. So here's your max. This is your a in this case. And so this f at a is bigger than or equal to all the other f at x's, if this is y equals f at x. And then minimum would just, if you flip the parabola over, you would have an example of that. So say this is a, and this is f at a. So with an absolute or a global max or min, you've reached the absolute bottom or the absolute top of the graph. The biggest output or the smallest output. Excuse me. The relative or local max and mins are basically your peaks and valleys. So you can have more than one of these. It doesn't have to be the biggest value on the entire domain, but it's the biggest value in some sort of interval about the number. So if you have, I think I'll just draw one picture for both of these. Maybe you have something that looks like this. Then anytime you reach a peak, that's going to be a local max. So this is a local max, this is a local max. I'm going to call this A. I'll just go left to right. This one's going to be a local min here. B, C. I need to extend this. And here's another, like about right here, D. So I didn't label A. A and C are local maxima, and B and D are local minima. But if you look at these arrows, there is no absolute max or absolute min, because this keeps getting bigger and bigger and bigger once you get far enough to the right, and this gets smaller and smaller and smaller. So no absolute max or min for this graph that I drew here. Okay? But this is the biggest in this interval around it. This is the smallest around it, so that's the idea here. So in this graph, here we actually have some function values we can use. Again, let's just assume everything's 1 unit here because I didn't label. So the relative maxima, the maxes are going to be the peaks, and so this one is going to be a relative max. We would have that function value is 3. And so what I say to do on these is you give the maximum value is actually the y value, or the output value. And so you would say 3, and then to be more descriptive, you would say what x coordinate that occurs at. The maximum is 3 at x equals -2. Okay, so that's for the first question. The absolute max, because of the arrows, there's none. And then the relative minima, so we have 2 minimums here, right? Or minima. This one is actually an absolute, but every absolute also automatically satisfies the relative one as well. So you're going to list this one twice actually. So here, this minimum, I should say, is 1 at x equals 1, 2, 3, 4. That's -4. And this one is 1, 2, 3, 4, 5, 6. Easier if I include the label. -6 at x equals 1. All right, but this one is actually the absolute as well. So this is the minimum value is the output, and then the at part is just where does the function attain that max or min. Okay? So that takes up a lot of room in the notes, but it's not that hard of a concept. All right, I'm going to take a little break right here, and then we'll talk about symmetry.